This is Rajkumar, Assistant Professor of Mathematics, GTN Arts College, Dindigul. In this lecture, we discussed about what is meant by vector space and its properties. Okay. Now, definition: a vector space is a non-empty set V of an object called vectors on which are defined two operations called addition and multiplication by scalars subject to 10 axioms listed below. The axioms must hold for all vectors u, v, and w in V and for all scalars c, d. First axiom, the sum of u and v denoted by u plus v is in V. Second axiom, that is a commutative axiom, u plus v equal to v plus u. Third, the associative axiom u plus v plus w equal to u plus v plus w. Next axiom, there is a zero vector 0 is in V such that u plus minus u equal to 0. Next, for each u in V, there is a vector minus u in V such that u plus minus u equal to 0. The scalar multiple of u by c denoted by cu is in V. Next, c into u plus v equal to cu plus cv. Next, c plus d into u equal to cu plus du. Next, c into du equal to cd into u. Next, 1 into u equal to u. Next, example for a vector space. The space of all 3 cross 3 matrices in a vector space. The space of all matrices is not a vector space. Next is definition. The subspace. Subspace is nothing but a subspace of a vector space V is a subset H of V that has 3 properties. First one, the zero vector of V is in H. Next, H is closed under vector addition. That is, for each u and v in H, the sum u plus v in H. Next, H is closed under multiplication by scalars. That is, for each u in H and the scalar c. Next, the properties A, B, C guarantee that the subspace H of V is itself is a vector space. Under the vector space, operations already defined in V. Next, some property, every subspace is a vector space. Conversely, every subspace is a subspace of itself and possibly of other large spaces. Next example, the space of 3 cross 3 upper triangular matrices is a subspace. The space of all matrices with integer entries is not. Next, zero space. Okay, zero subspace. The set containing of only the zero vectors is in a vector space V is a subspace of V called the zero space and is written as 0. Set bracket 0. Okay. Next, the linear combination. As the term linear combination refers to any sum of scalar multiples of vectors and span v1, v2, up to vp. The set of all vectors can be written as v1, v2, v3 up to vp. Next example, given v1 and v2 is a vector space V, let H equal to span of v1, v2 so that H is a subspace of V. Proof: the zero vectors is in H, that is 0 equal to 0 plus v1 plus 0 plus v2 to show that H is closed under addition. Okay, take 2 arbitrary vectors in H, say u and w. That is, u is a form of s1 v1 plus s2 v2 and w is the form of t1 v1 plus t2 v2. Clearly, the axioms 2, 3, 8 for the vector space V. Next, u plus v equal to s1 v1 plus s2 v2 plus T1 V1 plus T2 V2. S1 plus T1 into V1 plus S2 plus T2 into V2. Next theorem, if V1 comma V2 up to Vp are in the vector space V, then the span V1 comma V2 up to Vp is a subspace of V. We call span V1 comma V2 up to Vp the subspace generated by or spanned by. Okay, generated by or spanned by V1 comma V2 up to Vp. Okay, given any subspace H of V is a spanning or generating of a set V1 comma V2 up to Vp in H such that H equal to span of V1 comma V2 up to Vp. Okay, next definition, null space. The null space of an M cross N matrix A written as null of A, that is null A, is the set of all solutions of homogeneous equations Ax equal to 0. Next, an explicit discrimination of null A. There is no obvious relation between vectors in null A and the entries in A. We say that null A is defined implicitly because it is defined by a condition that must be checked. No implicit list or description of elements in n null A is given. Solving the equation Ax equal to 0 amounts to producing an explicit description of null A. Example, finding a spanning set for the null space of a matrix. Given the matrix A equal to something. Okay. Solution. The first step is to be find the general solution of Ax equal to 0 in terms of free variables. That is, rho reduced the augmented matrix A0 to reduced echelon form in order to write the basic variables in terms of free variables. That is a upper triangular matrix. The upper triangular matrix can be written as the system of equation x1 minus 2x2 minus x4 plus 3x5 equal to 0, and x3 plus 2x4 minus 2x5 equal to 0, and last one 0 equal to 0. Next, the general solution is x1 equal to 2x2 plus x4 minus 3x5, and x3 equal to minus 2x4 plus 2x5 with x2 comma x4 and x5 free. Next, decompose the vector giving the general solution into linear combination of vectors where the weight are the free variables. That is, column matrix x1, x2, x3, x4, x5 equal to 2x2 plus x4 minus 3x5, x2, minus 2x4, 2x5, x4, x5, that is equal to x2 into column matrix 2 1 0 0 0 plus x4 into column matrix 1 0 minus 2 1 0 plus x5 into column matrix minus 3 0 2 0 1. Okay. Next, the spanning set produced by the method is automatically linearly independent because the free variables are the weights on spanning vectors. Next, when null A contains non-zero vectors, the number of vectors in the spanning set for null A equal to the number of free variables in Ax equal to 0. Next, kernel and range of a linear transformation. The kernel or null space of such a T is a set of all U in V such that T of U equal to 0. That is, the 0 vectors in W. The range of T is the set of all vectors in W of the form T of X for some X in V. The kernel of T is a subspace of V. The range of T is a subspace of W. Okay. Next class, we have discussed about some theorems on vector spaces. Okay. Thank you.